Hello, I'm Dr. Fereydouni. It's my pleasure to present our paper entitled Fault-Tolerant Analysis Using Serial Triple Modular Redundancy (S-TMR) and TBCD Ultra-Low Energy Communication Protocol for Biosensors. This work was done in collaboration with Dr. Ait Mohamed at Concordia University. This work is about reliability of TBCD communication protocol. TBCD is an ultra-low energy communication protocol intended for implantable wireless body sensor networks, which stands for IWBSN. Here is the outline of my presentation. After a brief introduction to IWBSN, I present the main challenges of biosensors implanted inside the human body. Then I will give a brief description of TBCD protocol, followed by our contribution related to improvement of TBCD protocol using TMR, which is triple modular redundancy technique. We show how we converted the TMR technique from parallel to serial in order to save area and power consumption. And then we will conclude with the summary. Please let us have a quick introduction to IWBSN. This is a big step in human healthcare. Physicians and medical teams around the world are very much interested in implanting many tiny biosensors in different spots inside the human body, and monitor and analyze all related health information received from these biosensors in real time worldwide through the internet. And that's while the patients could enjoy and maintain their normal active lives without having to be hospitalized. These biosensors can permanently monitor health information such as blood oxygen, urine, glucose, pH, kidney status, heart status, brain status, and etc. Now let's see what are the challenges of these tiny biosensors. One of the most important characteristics of these tiny biosensors inside the human body is their size. They must be so small that they could be safely implanted inside the tissue of the human body without being rejected. Hence, these biosensors cannot carry large batteries with them. Therefore, they suffer from lack of energy resource to stay alive inside the human body for a long time. This slide illustrates different components inside a tiny biosensor, as well as power consumptions associated with each component. Based on some low-power examples that we have already referenced to our previous works, it shows that the transceiver component is the only component which is consuming the highest portion of energy conserved inside the battery. The power analysis shows that more than 99% of energy of the battery is consumed by the transceiver component. Yet there is no solution for IWBSN lifetime inside the human body, even using modern hardware technology. Therefore, TBCD communication protocol was proposed as a smart feasible solution in 2009 in order to significantly prolong the lifetime of these biosensors applicable to IWBSN. Now please let's get familiar with ultra-low energy TBCD communication protocol to see what it is and how it works. The TBCD technique works based on star network topology. This model illustrates an example of 8 sensor nodes and a central master node representing base station. Each node ID transmits its data to the master node only within its own associated time slot. Each time slot counts for a certain number of clock cycles, for example n clock cycles, with respect to the network clock frequency. The sensor data is a value within a range of minimum and maximum value. This value is mapped from its original range into its node ID range, which is specified by TI in this model. The node ID is always counting in range 0 to n-1 in our example here. Once the data counter matches the mapped sensor data in TI range, the transmitter wakes up and transmits only a short signal in ideal case to the master node or base station. This signal represents the original sensor data. The master node or base station, which is rich in power and performance, will receive this signal associated with that ID node and will detect the same value mapped in the TI range the same way, and then remaps this value from TI range back to its original data through the same mapping table. This slide illustrates some simulation results experienced in MATLAB Simulink area. It represents 16 sensor nodes, each sampling 8-bit random data. Sensor nodes are stimulated with integer random data in range 0 to 256. For example, here, the red circles from the top point to the sensor data, the same data obtained at the base station and sensor number 2. This graph shows the scalability and efficiency of the TBCD communication protocol and represents the relation between network clock frequency, maximum number of sensors, and the data range or resolution of data transmission. The higher clock frequency, the more number of sensors can be accommodated and higher data resolution capacity. Some levels of efficiency are depicted in this table using common available technology. For example, looking at the first column, in case of using a 4 MHz clock, the TBCD can cover up to 256 sensor nodes, each node capable of communicating 14-bit data with the base station. Now please let's see how the bit error rate in TBCD communication protocol has been mitigated using serial TMR technique. TBCD protocol, like any other wireless transfer protocol, may suffer from any SEU, single event upset, and could result in any missing or data corruption at destination side. These kinds of errors can affect TBCD behavior as illustrated in this slide. For example, sensors S1, S2, and S3 on the left side represent the correct data transmission to the master node, and corrupted or missing data shown on the right could be false results appearing in any of these types of errors. For example, multiple data arrivals for sensor number 1 as error type 1, missing data for sensor number 2 as error type 2, and wrong data received for sensor number 3, which will be detected by a checker as error type 3, and etc. For this purpose, to overcome these errors, triple modular redundancy technique is used in TBCD protocol in order to mitigate the bit error rate issue due to SEU phenomenon. TMR is a commonly used known technique to minimize the SEU effect. It votes on the outputs of 3 devices working in parallel at the same time, and thereby it requires 3 times hardware and consumes 3 times energy. Which in terms, on one hand, it is great benefit to decrease the bit error rate, but on the other hand, it is big disadvantage over the TBCD protocol design by paying 3 times more area and power. That's why we used our modified TMR technique by converting it from parallel to serial. And instead of replicating the hardware 3 times, we used the available timing budget already explained in the scalability and efficiency of the TBCD protocol. And this eliminated the twice extra hardware usage inside the human body, which in turn, it eliminates radiating extra electromagnetic waves toward the human tissue with respect to the FCC regulations. We used these definitions to design the TMR technique within the TBCD protocol. A network cycle encapsulates all sensor cycles in the network. The TMR cycle constitutes 3 sequential sensor cycles, and the TMR start signal always expects 2 subsequent TMR signals. This flowchart illustrates the flow of fail and path decision control for our serial TMR protocol in high level. The implemented serial TMR inside the TBCD design is verified in a simulation environment under random noise injection. Random noises were generated and injected randomly into the data being transmitted to the base station. Several tests are experienced, starting with 100 transfers up to 1000 transfers each time. This table shows the results before and after 1% noise injection to the data transmission, and it shows 100% fail to pass coverage. And this table shows the results before and after 5% noise injection, and the results in most cases show above 95% successful fault coverage. And by injecting 10% noise, the fault coverage tendency shows around 90% fail to pass. This increases the total pass results from 72% to more than 97%. Okay, please let's have a look at conclusion and see what we have covered so far. We started with an introduction to implantable wireless body sensor networks, or IWBSN, and then we investigated the energy issues related to the tiny biosensors inside the human body. Then recalling our TBCD ultra-low energy communication protocol, and we showed how we exploited the TMR technique in TBCD protocol in order to protect data transmission in harsh environments. Plus, we showed how we modified the TMR technique by converting it from parallel to serial and implemented inside the TBCD hardware design. And then putting these all together under noise interference in simulation, and achieved up to 97.5% pass in fault coverage under 10% noise interference. And this concludes our presentation. Thank you.